Our next topic is hashed inverted page table. Here, first from the CPU generated logical address is converted into its binary equivalent. Then step 1 is from the CPU generated logical address that is converted into binary. So from logical address generated by the CPU, the page number that is denoted as small p suffix j will be retrieved. Next, step 2, the process identity number that is known as PID of the corresponding page number will be retrieved from process control block. Here, so first step is from logical address generated by the CPU, we will have to convert it into the binary, and we know that from the binary number how we can get the page number. The process was, the binary number was divided into two parts using the page size. The left part was page number and right part was page offset. So that was the procedure to compute the page number. Next, the process identity number of the corresponding page number will be retrieved from the PCB. The process identification number is denoted as PID. Step 3, this PID and P suffix j will be converted into binary equivalent. The two binary string will be merged to get a single string. The resultant string then will be converted into decimal equivalent, that is denoted as caps X. Next, step 4, consider the number of entries in the page table equal to the nearest prime number of the number of frame available in the memory. Step 5, apply hash function that is denoted as hx equal to remainder of x comma a, where a equal to number of frame in page map table. Step 6, the result of the hash function will be denoted as V, which indicate the corresponding frame number of the pattern PID, EJ. So this is the sixth step by which the hash inverted page table is implemented. So first CPU generated the logical address that is converted into binary. From that binary number, the step 1 was to compute the page number. Then we will find the process identification number, that PID from the process control block. Then PID and PJ will be converted into binary. Then these two binary string will be converted to get a single string. The resultant string will be converted into decimal to get the value X. Next, step 4, we have to consider the number of entries in the page table equal to the nearest prime number of the number of frames available in the memory. That means if there are 100 page table entry in the page table, then we will consider 97, because 99 is not prime, 98 is not prime, 97 is the prime. So the nearest prime number of the number of frames available in the memory, that is the concept of the nearest prime number. Then we have to apply HX. Apply HX means remainder of X comma A. Now the result of the hash function will be denoted as caps B, that indicates the corresponding frame number of the pattern PID and PJ. Now we will see a numerical example. Suppose the value of X equal to 24. That means PID plus PJ. This X is this one. Now the value of A equal to 11, that is frame number. So V will be 24 by 11, that means remainder will be 2, remainder of 24, 11, so we will get 2 as a result. Now in another example, suppose A equal to 11, X equal to 35, so we will get 35 by 11, that means 2. So from this example, the conclusion is that there are two pages of two different processes that are stored in the same position. So there will be a collision which can be resolved by applying linked list. How we will solve that? Suppose this is your linked list. So this is 0, 1, 2, 3, 0, 1, 2, 3, 4. Now in here it will store 24, 11, that means PID plus PJ. Now in the same location there will be another process with another page number. So we will just linking the address, that will be QID plus PJ. So this is the way by which we can avoid the collision. The example or the hashed inverted page table is used by IBM RS 6000 computer and AS 400 computer. So this is the whole concept of hashed inverted page table. Our next topic is Bilities Anomaly. We will explain the Bilities Anomaly with an example. suppose we have given a page reference string like this one, 1 2 3 4 1 2 5 1 2 3 4 5. Now we have given 3 frame and we are told calculate the number of page fault in FIFO page replacement technique. So there will be 3 frames. Here will be 1. Next there will be 1 in second most position. There will be 2. Next in third case there will be 1 2 3. Next the new page is 4. In FIFO page replacement the first position will be replaced, so it will be look like this one, 4 2 3. Next there is a new page that is 1, so 1 will replace the second position, that means it will be look like this one. Next there is a new page 2, it will replace the third position. Next there is a new page, so it will replace the first position. Next there is page number 1, so there will be no page fault. There will be 2, so there will be no page fault. Next there is new page, it will replace the second position. Next there is a new page, so it will replace the third position. Next there will be no page fault because 5 is already present, so the number of page fault taking 3 frames will be 9. Now consider this similar page reference string and now we are given 4 frame. Now we have to calculate number of page fault in FIFO. So 4 frame means here are 4 frames, so first position 1, next there will be 1 and 2, next 1 2 3, next 1 2 3 4, next 1 is already present, so there will be no page fault. Next page is 2, already present. Next page is 5, so 5 will replace the first position, that 5 2 3 4. Next the new page is 1. 1 is not present here, so it will replace the second position. Next 2 is the new page, so it will replace the third position. Next there is a new page, so it will replace the fourth position. Next there is a new page, so it will replace the first position. Next there is a new page, it will replace the second position. So taking 4 frame, the number of page fault will be 1 2 3 4 5 6 7 8 9 10. So number of page fault equal to 10. So from this given problem we can see that number of page fault is taking 4 frame is greater than number of page fault taking 3 frame under FIFO page replacement technique. This exceptional condition is known as Bilities Anomaly. Why this is an exceptional case? Because if we increase the size of page frame or the number of page frame, then the page fault will be reduced. But here you can find from the problem that we have increased the frame number, but the page fault is increasing. That's why it is an exceptional, and this exceptional condition is known as Bilities Anomaly. Our next topic is memory interleaving. The main memory is partitioned into separated independent memory module and address distributed across the module. This scheme is known as memory interleaving, which allow concurrent access to more than one module. The interleaving of address among M module is called MOA, memory interleaving. It is of two types: high order or S axis, low order or C axis. Now come to what is S axis or simultaneous access. Here, higher order M bits are used to select the module, and remaining N minus M bits are used to select the address within the module. Now, what is low order? Here, lower order M bits of the address select the module, and remaining N minus M bits are used to select the address within the module. Now we'll explain this memory interleaving by taking a numerical example. Suppose a numerical example is given like this one, where memory is 64K. It is a 4-way memory interleaving. Now draw the diagram for high order memory interleaving. So here the value of M is 4 because it is a M way interleaving, that means 4-way interleaving. The memory size is given here is 64K. 64K means 2 to the power 6K, and this will be 2 to the power 6 into 2 to the power 10, that means 2 to the power 16 bytes. The value of n minus m will be 16 minus 4, that means 12. So this will be, total is n, the value of n is 16, where the value of m equal to 4 and n minus m equal to 12. Now there will be a decoder by which we will separate the module 1, module 2, module 3, like this way. We will go up to module 16, and this n minus m will be used to select the address within the module. So this is all about high order memory interleaving.